And now on a topic near and dear to my own heart, celestial mechanics, the study of the mathematics and physics of systems of particles that attract one another through the force of gravity. In this problem we have three such particles. I've labeled them Earth, Moon, and Sun, but it doesn't really matter, I just had to give them some names. And we're looking at a situation where one of those bodies comes in between the other two. It's called a syzygy in celestial mechanics, or in astronomy, it's often called an eclipse. So, we have a relationship here between the potential energy, the total potential energy of that system, which we can measure in the SI unit of energy, joules, and the distance between that third body and the line joining the other two. We're going to call that r, and we're going to measure it in meters. The first question is, how can we find the average rate of change of potential energy with respect to a change in distance between 2 points on this graph? First of all, average rate of change, no matter where and when you see it, is synonymous with a slope. Specifically, it's a slope of a secant line. And that secant line is going to connect the point at r equals 0 meters, highlighted in red on the graph and in the data table, and the point r equals 1 times 10 to the 10th meters, also highlighted in blue on the graph and on the data table. So what's the average rate of change? It is synonymous with the slope of a secant line being a line that connects those 2 points on the graph. Remember, before we can talk about slope, anytime we talk about slope, we have to have a line first. So slope of what is the question, and that what is always going to be a line. For average rate of change, it's this secant line that connects those 2 points. So we've reduced this problem now to just the question of finding the slope of that line that joins the 2 points that we've labeled. And like any good slope, it's measured as a difference in y values. So subtracting these y values gives you negative 1.333. Divided by a difference in x values. Subtracting the x values here gives you 1. And so when that arithmetic settles, we get negative 1.333. Is the slope of this green secant line. Now, what are the units of that slope? Like any slope, the units, because slope is rise over run, are the units of the vertical quantity divided by the units of the horizontal quantity. Since our vertical quantity, potential energy here, is measured in 10 to the 10th joules, in other words, in 10 billions of joules, that's going to be the numerator of my units, where the denominator of my units is the units of my horizontal quantity, 10 to the 10th meters. So the units of my slope are 10 to the 10th joules per 10 to the 10th meters. But we can make that a little simpler, because we have that 10 to the 10th both top and bottom. We can cancel it out and see these units more simply as just joules per meter. Negative 1.333 joules per meter. A physicist could actually tell you that joules per meter are actually a unit of force. A joule per meter is actually a newton. We don't have to know that. For this problem, we just have to know that that's where our units come from. We divide the units of the vertical quantity by the units of the horizontal quantity. So the average rate of change here is negative 1.333 joules per meter. Next we turn the page, and instead of asking about an average rate of change, we want to ask about an instantaneous rate of change. So because it's still a rate of change, we're still talking about a slope. The difference, though, is an instantaneous rate of change is not the slope of a secant line, but the slope of a tangent line. So that's the big change in wording and in philosophy in this problem. And that tangent line is taken at the point r equals 1 times 10 to the 10th meters. So that's the point labeled in red on the graph and highlighted in red on the data table. But, crucially, we only have 1 point to work with in this problem right now. And so we can't have a secant line because a secant line joins 2 different points on the graph. Instead, when we talk of instantaneous rate of change, we speak of a tangent line, which touches the graph of our function at 1 point only, locally. So what we have to do in this problem is we have to sketch in that tangent line so that we can use the graph to estimate this instantaneous rate of change. So step 1 is just sketching in that tangent line as best you can. So your answers are going to vary probably a little bit depending on exactly how you draw your line. I tried to make mine here as accurate as possible, but even I can only do so much with a picture like this. So there's our tangent line. And we've again boiled this question down to the question, what is the slope of that line that we just drew? That slope will be, by definition, the instantaneous rate of change of this function at the point that's labeled. Well, to find the slope of a line, we still need a second point, besides the one that's marked in red. So let's just go hunting for a second point. But the best we can do with that second point is estimate its coordinates, because we're going to have to read them off of this graph. I'm going to pick the point which is easiest for me to measure, That second point that I choose, just for kicks, is going to be the point which actually is the intercept of that line back on the vertical axis. And I can estimate its coordinates as being about 0, 1.78-ish. And again, I'm eyeballing that coordinate, so I might get something a little different than you get on this problem. But now that we have those 2 points, we have the point that's marked in red that's on the graph, we have the green point which we just labeled as the intercept of the line that we sketched, the tangent line. Those 2 values can be used to find the slope of this green line, the tangent line, in the usual fashion. By subtracting the y-coordinates, I get negative 0.613. Subtracting the x-coordinates, I get 1. And then dividing the former by the latter. After that arithmetic is done, we get the number negative 0.613, which is the slope of the tangent line, and therefore the instantaneous rate of change of this function. At least it's our estimate for the instantaneous rate of change at the point r equals 1 times 10 to the 10th meters. What are the units? Well, again, this is still a slope, just like it was when we talked about the average rate of change. So its units are the vertical units on this graph divided by the horizontal units on this graph, 10 to the 10th joules divided by 10 to the 10th meters, which simplifies again to joules per meter. So this number, negative 0.613 joules per meter, is our estimate for the instantaneous rate of change of potential energy with respect to distance at r equals 1 times 10 to the 10th meters. So now we've measured an average rate of change. We've measured an instantaneous rate of change. Our last task is to figure out how to unite those 2 pictures. So remember, our average rate of change was joining the points at r equals 0 and r equals 1, and it was about negative 1.333 joules per meter. The instantaneous rate of change that we just measured was the slope of this tangent line taken at r equals 1, and its value was about negative 0.613 joules per meter. These 2 numbers are pretty different. The question now is, can we find an instantaneous rate of change that is better approximated by an average rate of change? In other words, can I find a secant line on this graph whose slope is more similar to the slope of the tangent line that we drew? So now this comes down to an artistic question. How do I draw a blue line on this graph that connects 2 different points that has roughly the same slope as the line which is shown in green? So to do that, I'm just going to eyeball it. I'm going to take a line which is parallel to the green line and just draw it so that it slices through 2 different points on the graph. If the lines are parallel, that means their slopes must be the same. The last question then is, what secant line is this? What 2 points did we happen to cross on this graph? Your answers may vary, but I happen to set mine up just so that the points that it crossed are actually at 0.5 and at 1.5. The reason I had it crossed there is I wanted to remind you of the lesson, that the best way to estimate the instantaneous rate of change accurately is to use a symmetric difference. The best estimator that we have here for the instantaneous rate of change at r equals 1 is the average rate of change from r equals 0.5 on the left to r equals 1.5 on the right. And if we use the data table to actually get values to estimate that slope of the secant line, the numerator, subtract the y values, negative 0.696. The denominator, subtract the x values, 1.0. Divide those out. Negative 0.696 is the slope of that secant line, which actually is pretty close to the slope of the tangent line that we got in this problem. So moral of the story, if you want to estimate an instantaneous rate of change exactly, the best thing you can do to estimate it is to use a symmetric difference from that point. Use 1 point on the left and another point on the right.